All right, so we talked last week about intermolecular forces and about these different ways that molecules attract each other. Now we're going to look at some of the consequences of that with regard to like how it actually affects something and how we can think about that. The effect that we're going to focus on is vaporization. So we talked a little bit about vapor and vaporization when we talked about gases, and then we talked a little bit about it. We looked at boiling points when we looked at intermolecular forces, but we didn't really talk about what vaporization really means. So vaporization itself is very simple. That's just the phase transition from liquid to vapor. So as something moves from a liquid phase to a vapor phase, it undergoes vaporization. What's happening then? So how can we describe at the molecular level what happens when a substance transitions from a liquid to a vapor? Like what is physically happening to it, to the molecules?
Liquid state, it assumes the shape of the container, but not the volume. So as it vaporizes, it will then take up the shape and volume.
Okay, that's true. So what's happening to the molecules that allows that to happen? Yeah, Julie.
Aren't they moving around faster and separating?
Well, not the first, but the second. So moving around faster, we have to be careful of because moving around faster is related to kinetic energy, which is related to temperature. But the second part is correct. They're separated. So what's breaking or what's allowing them to become separate from each other? Is it though? It's not quite bonds. It's something else. Like what holds water molecules together to each other? If it's not bonds, I mean the bonds are what hold the O's and the H's together, but what holds the water molecules together? It's the intermolecular forces, the forces between molecules or among molecules. And the ones in water would be hydrogen bonding, which we said was kind of a confusing term because it sounds like bonds. So when vaporization is happening, those intermolecular forces are breaking. Right? We have to break the intermolecular forces to vaporize something. So does that make this a endothermic or exothermic process? Do we have to put energy in, or does energy come out? In. We have to put energy in to break those interactions. So this is an endothermic process. What's the opposite of vaporization? Condensation, right. A vapor becoming a liquid. Is that endothermic or exothermic? That's exothermic. So when the vapor becomes a liquid, energy is given off because all of those intermolecular forces, interactions that happen, like hydrogen bonding, are, as soon as they form, they're giving off energy. All right. So, have you heard the term volatile or volatile? What does that mean? I mean, yeah, but specifically with respect to vaporization. So it's substances that are easily vaporized. They become a vapor very easily. So what else could we say about a volatile substance in terms of its intermolecular forces?
Does that mean it's the smallest type of, or the
Yeah.
biggest type of intermolecular force?
Right, that we would say in general, these are going to have weaker, something that we call volatile is probably going to have weaker intermolecular forces because it is able to form a vapor that is to dissociate easily. So let's think about some things that we think are volatile. Is water volatile? Do we describe water as being volatile? And this is a relative term. There isn't like an official measure of volatility. Do we describe water as volatile? Not really, right? What is something that we would describe as volatile? Like a liquid that is volatile. Rubbing alcohol, sure. How do you know that it's volatile?
Because if you like clean something with it, it evaporates here.
It evaporates really quickly and easily, right? And so that tells us that probably rubbing alcohol is going to have weaker intermolecular forces than water, which it does. It actually does hydrogen bond, but because of all the carbon and hydrogen in there, it's not quite as, doesn't make quite as strong of interactions. Most nonpolar things we would describe as volatile. So stuff like gasoline or butane, those types of solvents are usually very volatile. And even some very heavy things that we might not think of as volatile right away. One of the reasons mercury is so dangerous as an element, mercury is like a silver liquid, and it looks cool because it's like silver, but it looks like metal, but it's a liquid at room temperature. But one of the reasons it's so dangerous is because it's volatile. Mercury only attracts other atoms of mercury through dispersion forces, since it's just a neutral atom. And so it can make mercury vapor really easily. So whenever there's liquid mercury around, there's also mercury vapor around, and that you can inhale, and that can be really dangerous. So that's why we're always really careful not to have open containers of mercury. If there's a mercury spill, we have to get special equipment to clean it up right away, because those vapors can be really dangerous. Okay. So remember from the gas chapter that when we talk about molecular speed and we talk about energy, kinetic energy, that it's actually are always in a range. So there's a picture here. If I can find it. Here. All right, so if you look at a distribution of energy, the molecules don't all have the same kinetic energy. We talked about that in the gas chapter, but that's true for liquids too. At a particular temperature, the average kinetic energy is proportional to the temperature, but there's always going to be a range. And some molecules will have more energy and some molecules will have less energy. So there is a particular amount of kinetic energy that is needed to escape. What does it mean by escape? Escape what?
The liquid form.
Yeah, which is given by those intermolecular forces. So once a compound has enough kinetic energy, or once an atom or a molecule has enough kinetic energy, it's going to start moving so much that it becomes no longer bound by the intermolecular forces network in that substance. So it's going to be able to evaporate or to vaporize because it can escape the intermolecular forces. So here is a graph of two different temperatures. The blue is the lower temperature and the red is higher temperature. Lower temperature on the left, higher temperature to the right. And you can see that in which one of those situations, temperatures, has more molecules that have enough kinetic energy to escape. The higher temperature or the lower temperature? The higher. Do you see that? Everybody see that? The area under the curve, because this is like a histogram because it's fractions of molecules, the area under the curve to the right of the line there is greater for the red than for the blue. And so that tells us that at the higher temperature, more molecules can escape that intermolecular force network. So if we think about something like water, what does that tell us about what's actually happening in a sample of water? If we have a sample of water at room temperature, are there some water molecules that have enough kinetic energy to escape from the water network?
Yeah.
There are. How do we know that? I mean, we know there's a distribution.
Because eventually water evaporates.
Eventually water evaporates, right? Have you all seen this? You spill water, eventually it goes away because it's evaporated. Or you leave water out, eventually it's going to evaporate. That's not because water is particularly volatile, but because as long as there's some fraction of molecules that can escape, eventually they will, and then more will get that in that distribution, escape, and so on. So any sample of water at any temperature, really, there's going to be some vapor, some vapor there. And that's what we call vapor pressure. So there's an equilibrium present between water molecules in liquid, that there's going to be some that have enough escape velocity or escape energy to get out of there. And then once there's so much of a gas, of a vapor pressure, that creates a pressure down that more water molecules can go back in and form more intermolecular forces. So that's called a dynamic equilibrium. It's at this point, the rate of evaporation is equal to the rate of condensation. So there's always going to be water molecules evaporating. There's always going to be water molecules condensing in this sample. All right, so a sample of liquid water looks like this, not like this. It's always at this dynamic equilibrium. And this these molecules that are up there in the vapor are creating a pressure, just like any gas does. They're susceptible to gravity, and they are exerting a pressure down onto the others, and that's why we call that a vapor pressure. Remember from back in the gas chapter, we talked about when you collect a gas over water, you have to correct for the vapor pressure of water, and that creates a partial pressure. That's that partial pressure. There's always going to be water molecules above the sample, and the hotter it is, the higher the temperature, the greater that vapor pressure is going to be. So that makes something interesting going on here. Just skip a little bit here. And that actually gives us a measure for what we call boiling point, like what boiling point actually is. So take a look at these graphs of vapor pressure, which is how much pressure is the vapor above a liquid exerting on the liquid, versus temperature. And what's going on here? The boiling point is given in degrees Celsius at a particular point that we call the normal boiling point. What is that? Why is that spot important on this graph? So when each of these lines crosses that black line, that's called the boiling point. Why? What's going on with that black line that's special? Chris?
Is that 0 atmosphere? Or 1?
1 atmosphere.
Atmosphere, there we go.
Yes. So everybody see that? That line is at 760 torr, which is 1 atmosphere. So what does that mean? Why? What does that mean if the vapor pressure is 1 atmosphere?
Is that standard pressure?
That's standard pressure. So what's happening in the sample at that point, that molecule?
There's a balance of the forces of condensation and evaporation.
Right. Well, I mean, there's always this dynamic equilibrium, but yes, at that point, what we call the boiling point is where the vapor pressure equals the atmospheric pressure. And since we standardize everything at standard pressure, we call it at the atmospheric pressure at sea level, which is 1 atmosphere, 760 torr. So when the vapor pressure reaches that amount, that's what we call the boiling point. So the atmospheric pressure is no longer pushing the vapor back down into the liquid because the vapor itself has the same vapor pressure as that's around it. And we know some things about how this affects in different pressures too. So like what happens with water if you are way up in the mountains, if you're at high altitude, if you're like in Denver or somewhere like that, what happens when you boil water?
It's a lower boiling point.
Yeah, it's a lower boiling point. So if you have less atmospheric pressure, you are, let's pull this back into the notes so we can draw on it. It's very large. Better. Okay. All right, so if you are at high altitudes, then your atmospheric pressure is, let's say, here. So now water is actually boiling at a lower temperature. And that's why if you look at like packaged foods, they sometimes have special high altitude directions. I don't know if has anybody ever noticed that? Let's say like at high altitude, cook it for 10 extra minutes or whatever. And that's because the water is actually boiling at a lower temperature. So stuff takes longer to cook. So people who live at really high altitudes, especially like in South America and the Andes and stuff, it's become really popular to use pressure cookers where you can actually have all the stuff inside a closed vessel that pressurizes so that you don't have to worry about the fact that your atmospheric pressure isn't really pushing down enough to give you a high temperature in your boiling water. This is also how we can think about things being more or less volatile. If you look at the comparison between some solvents, diethyl ether and ethanol, compared to water, we would call those both more volatile than water. So what does that really mean? Why are they more volatile than water? There's a couple different things going on there. What's some reasons that they're more volatile than water? Yeah, Chris?
They require a lower temperature to get to a boiling point at the same pressure, the same standard pressure as water.
Yeah, so they're going to have a lower boiling point. That's part of it. What else?
I was going to say the same thing, but I was just going to say they probably have weaker intermolecular forces because their boiling point is.
That's true also. So that is why they are. And if we look not only at the boiling point, but at anywhere else, at any other temperature, like let's say room temperature. Room temperature is like here. So you can see that at room temperature, diethyl ether has a very high vapor pressure in comparison to water. And so that tells us that if we have those samples at room temperature, there's going to be a lot more vapor of the diethyl ether, which is a common laboratory solvent because it's so easy to evaporate, but it's also kind of dangerous because that vapor is very flammable. If you've ever heard of just ether as a solvent or as yeah, that's what that is. It was an old-time anesthetic. It's not a good anesthetic because it would kill people and usually make you really sick. Even if it didn't kill you, it kind of acts a little bit more like alcohol. So you would have all those toxicity issues, and you have kind of like a hangover issues when you come out of the anesthetic. But it was one of the first things that was discovered, and it was certainly better than surgery without any anesthetic. So at the time, it was probably worth doing. But yeah, it's very volatile. We always use it in the fume hoods now. If you talk to older folks, they always have stories about like back in the 60s or whatever, people would be smoking in the lab, and somebody would open a bottle of ether like on the other side of the lab, and then there'd just be like flames shooting through the lab because of the flammable vapors. That never I'm old, but I'm not that old. Nobody ever smoked in labs around me. So that's how we can describe boiling. Now I'm going to show you this next thing, but it's not something that you'll see on the final, I don't think. If it is, it's something I would not expect you to know, but it's something called a Clausius-Clapeyron plot. And it is a way to experimentally determine the heat of vaporization, so the amount of energy it takes to vaporize a mole of a given substance. And what you do is you measure the vapor pressure at different temperatures. And then you construct this plot. It's a log plot, so the log of the pressure versus the reciprocal of the temperature in Kelvin. And what ends up happening is you could take these experimental data and get these dots, and then get a trend line. And from that trend line, you can calculate the heat of vaporization, how much energy it would take to vaporize a mole of that substance, which of course is proportional to the strength of those intermolecular forces. Anytime we can get identifying information like that from experimental data, especially relatively easy to obtain experimental data, is really good because this is a fairly easy experiment to do, and then you can measure the heat of vaporization of your stuff. We're not going to worry about the calculations with that. I don't think it's in the homework, but if it is, it's just plug stuff into an equation and then solve for it. But let me know if you have trouble with that. Okay. So another thing to know about boiling is if you boil water, as you add heat, as you would expect, you increase the temperature. But once you get to the boiling point and the water starts boiling, you stop increasing the temperature until you've boiled all the water and have created water vapor. So the temperature of water, of liquid water, can never exceed 100 degrees C. Because what happens then?
It becomes a bit more vapor.
Yeah. So any more energy that you put into some water that's at 100 degrees is going into splitting up those water molecules from each other and boiling. So right when you reach 100 degrees, you haven't really started boiling because you need to put in more energy to actually break all those interactions. Another thing that you notice in this plot, even though there's no scale on the x-axis, is that the slope of this line here is shallower than the slope of that line there. What does that mean? What do the slopes of those two lines have to do with anything? Or what do they tell you? What do they tell us? Chris?
The rate at which the water in that form can accept energy.
Yeah, basically. It's something called the heat capacity or the specific heat. Those terms can be used a little bit interchangeably. They're not technically the same. But liquid water has a heat capacity of about 1 calorie per degree C, per gram degree C. So a gram of water, to move up 1 degree C, takes about 1 calorie of energy. So if we compare liquid water on the left to steam on the right, does steam require less energy to heat to the same temperature or more energy to heat to the same temperature? Less, yeah, because it's a steeper slope. So we would say that that steam has a lower heat capacity than liquid water. And in fact, liquid water has an abnormally high heat capacity. You can put a lot of energy into it before it changes temperature, and that's one of the reasons that it sustains life on this planet so well, because it can regulate temperature through the oceans. All right, so putting all this together, we can look at something called a heating curve. Which looks like this, and it's tracing what's happening to the water as we continue to put energy in. So it's a heating curve. It means we're adding heat. So the x-axis is not temperature, but heat added, putting in heat, putting in energy. And then the y-axis tells us the temperature changes. So if we start way down at minus 25 down here, we add energy, and the adding of that energy causes the ice to heat up. To heat 1 mole of ice from minus 25 to 0 takes about a little less than 1 kilojoule per mole. Okay, then we've got melting. So we got to put in more energy to melt that ice. And to melt, again, a mole of ice takes 6 kilojoules per mole. So it takes about 6 times the energy to melt a mole of ice that it does to heat it from minus 25 to 0. So then once we're at 0, we heat the water up some more. Now we've got liquid water. It's all melted. We heat the water up to 100 degrees, and it takes 7.5 kilojoules per mole to get water from 0 degrees to 100 degrees. But it is not boiled yet. It's just heated up. So if we actually want to boil all that water, we have to put in an additional 40.7 kilojoules per mole. And one thing I like about this diagram is it is actually to scale. So you can see it takes a whole lot more energy, right? Lots, like almost, 7 times the energy, almost 7 times the, 6 times the energy to get from, or to boil the water that does to heat the water up from 0 to 100. So it takes a lot of energy to boil water. That's another reason that water is special, is because that heat of vaporization is fairly high. That really high heat of vaporization is also a function of the intermolecular forces. So then once it's vaporized, we can heat up the steam and go from there. So that's what we call a heating curve, and it just shows us what's going on as we heat up the water. Another thing we can look at is called a phase diagram. Have you seen phase diagrams before? Some people, maybe, maybe not. Okay. So phase diagram is a little bit different. Rather than looking at heat input versus temperature, temperature versus heat input, we're looking at pressure versus temperature. Because as we just said, pressure affects these properties in itself. So it's not enough to just look at the temperature unless we assume the same pressure. So when we look at something like a heating curve, we're just assuming everything's at standard temperature and pressure. But if pressure becomes a variable, then things can change a lot. So here is a heating curve for water that is not to scale, because it actually ends up being this kind of giant thing. But it's condensed in a weird way so we can see everything. But pressure is on the x-axis, or the y-axis, and temperature is on the x-axis. So at our standard temperature and pressure, which is like here, this is where, like, along this line we could say is where we experience water primarily. So if we get below 0 degrees, it becomes a solid. Once we cross 0 degrees, we cross the solid liquid, what we call the fusion curve, and we make a liquid. Once we get to 100 degrees, we cross the vaporization curve, and then above 100 degrees, we are just in the gas, so we have a gas. So if we have standard pressure over here and high temperature, we have gaseous water. So now let's see what happens when we change the pressure. We're going to really change things a lot. So if we drop the pressure way down to here, what happens if we heat and cool water like in this realm, in this range?
It requires a lower temperature in order to melt it.
Solid to gas instead of solid.
Yeah, and that's the biggest thing is we're no longer accessing liquid water. So below this particular pressure, which it's actually quite a low pressure. It's not as close to 760 as it looks. It's a very low pressure. But below that pressure, we can no longer have any liquid water. So at low temperature, we have solid water, and then as we cross into a higher temperature, the ice sublimates, which means it goes directly from solid to gas without ever passing through the liquid phase. So you can only access the liquid phase of water in this range.
What's supercritical fluid?
So above the pressure and temperature of this point here, which is called the critical point, we have a new state of matter called a supercritical fluid. There's debate as to whether it's actually a new state of matter, but it's basically a different type of a fluid that has some properties of liquid and some properties of gas. Supercritical fluids generally, I mean, it's hard to define them as one thing, but the usefulness of supercritical fluids is that they have some properties of liquid, some properties of gas, but they have different properties from either the liquid or the gas. So one good example of a supercritical fluid that's used a lot is carbon dioxide. You pressurize carbon dioxide, you can make a supercritical fluid. So you can take carbon dioxide gas and pressurize it, and instead of making dry ice, you make this thing that kind of looks like a liquid. But it has very different properties from other liquids that we know. And it turns out to have very, very good extractive properties. So a lot of decaffeinating things like decaffeinated tea, decaffeinated coffee can be done with supercritical CO2 because that supercritical fluid can make its way into the substance. It can dissolve the caffeine and then extract it out without damaging the structure as much as another type of a solvent might. So it's used in that. It's used in a lot of types of flavor extraction. There are distillers now, like making things like gin, that use supercritical CO2 to extract more of the flavors from the different botanical ingredients and things like that. So that's what supercritical fluids are at very high pressures usually, and usually fairly low temperatures. Water is a little bit different, but very high pressures you can make these things, these supercritical fluids. So just to give you a sense of where these things are, because this does say it's not to scale, this thing here is called the triple point of water. That is at 0.0098 degrees C and 4.58 torr. Right, so very low pressure and right around 0 degrees. If you have a sample of water at that point, you will have all three phases of water together at the same time. You'll have some solid water, some liquid water, some gas water, all together. And that's what the triple point is. So other substances also have phase diagrams like this, but different types. So if we look at a couple like iodine and carbon dioxide, here's iodine's curve. One thing that you notice about iodine's curve is the fusion curve, that is the liquid-solid separating curve, is a different angle from water's, which means that it's going to act a different way under pressure. So let's go back to water just as a comparison. Where's water? Okay. So that means that let's say you're here and you've got some ice. If you pressurize that ice, if you keep the same temperature but you pressurize the ice, that means you go up in pressure. Eventually you cross over that line. What does that mean? It becomes a liquid. So if you compress ice while keeping it at the same temperature, you should be able to turn it into a liquid. That's somewhat unusual. Most substances have a more dense solid phase than a liquid phase. And so when you compress it, it goes the other direction. So iodine, look at its fusion curve. If you have some liquid iodine and you compress it, it will solidify because this curve is now at this angle. Does that make sense? So depending on the angle of those curves, it tells you what happens if you compress it or if you heat it. Now with iodine, we are generally kind of over here because this is at higher temperatures here. So its triple point is again at lower pressure but at a considerably higher temperature. And then comparing that to carbon dioxide, at carbon dioxide at standard pressure at 1 atmosphere, we miss the liquid phase completely, which we know because if we have dry ice, which is carbon dioxide, and you let it sit out, it doesn't melt, it sublimates. It turns into carbon dioxide gas. And so that carbon dioxide gas then is, if we're melting it, that means that we're over here. And so here at carbon dioxide, actually at right around room temperature, just above room temperature, if we pressurize it high enough, 73 atmospheres, which is high pressure but not crazy, you can make machines that do that, you can fairly easily access that supercritical CO2. Above about 5 atmospheres, you can get liquid carbon dioxide. Okay, so here's some questions about reading phase diagrams. Phase diagrams don't have to be just about different phases or solid, liquid, and gas phases. So this is a phase diagram of sulfur. Sulfur can be a vapor. It can be a liquid. It can also be a solid, which is how we normally think of sulfur. But sulfur has two different solid phases. One of them is called the monoclinic, and one of them is called the rhombic. So the question is, which phase is the higher pressure, or which form is the denser form of sulfur? What is the denser solid form of sulfur, the rhombic or the monoclinic phase? The rhombic is. How do you know? That's just a guess? Okay. Anybody else? Why does the rhombic have to be the denser phase? Chris?
It takes up more of the, it will be a rhombic in a wider range of pressure.
Almost. But specifically it's, Alex, do you want to add?
I was gonna say because if you decrease the temperature, it becomes more dense as it becomes more of a solid.
So the more dense thing is correct, but it's not the temperature that leads to that, it's the pressure. So if we take if we look at the difference between these two, so we just like start at some spot like here. If we increase the pressure, we will always eventually make the rhombic phase. And if we're in the rhombic phase and we increase the pressure, we'll never transition to the monoclinic phase. So if by compressing something you make it more dense, that tells us that the rhombic phase has to be the more dense phase, because any of the other phases, if we compress it, we will eventually get to that rhombic phase. And then the other question here is, below what pressure does solid sulfur sublime? So if you want a condition where solid sulfur goes straight to gas without making a liquid, what pressure do you have to be below?
0.027 millimeters of mercury.
Yeah, 0.027. So you have to be below here so that you miss the liquid phase. These are both solid phases, and both of these phases, so let's say you're right here. Whatever phase you're in, if you increase the temperature, you sublime. You go straight from solid to vapor without hitting liquid. Anything above that that pressure, you will form the liquid before you form the gas. And so you will not sublime, but you'll melt and then boil. Okay. Here's another example. This is actually a phase of kind of a weirder phase diagram of water. If you go up to the really, really high pressures, there are actually a bunch of different ices, different structures of ice from the standard ice 1 that we all know and love. Just different ways of water packing. And so the question is, so first, what three forms of ice are present at the triple point marked O? So this point that's marked O here, if you were to get to exactly that pressure and temperature, whatever it is, which three phases would you have?
It's 2, 3, and 5.
Yeah, 2, 3, and 5, the ones that all have a boundary right there. Good. Next question, would ice 3 sink or float in liquid water? Here's ice 3. Would ice 3 sink or float in liquid water? Well, what determines if something sinks or floats? Density. So is ice 3 more or less dense than liquid water? It is more dense because at the water ice 3 boundary, if you increase the pressure, you go from water to ice 3. So that tells us that the ice 3 is more dense. If the line went back this way, then it would be less dense. So it's more dense, so it would sink in water.
That's why ice 1 is less dense than liquid water, because the angle of the...
Right. Ice 1 is less dense than liquid water, and you can see that because if you compress ice 1, you can turn it into water at the same temperature with higher pressure. And then just to finish this up, and then we'll take a break. You can see one reason that water is so special, and we've seen this graph before, but now that we know a little bit more about this stuff, here's a whole bunch of different hydrides of elements, so elements with hydrogen. You can see the general trends are pretty much what we would expect, that as things get bigger, their boiling points go up. Their intermolecular forces get stronger, their boiling points go up. Then we've got these kind of 3 outliers here that are way higher than they should be. Why are those 3 way higher than they should be? The hydrogen bonding. So you have, these all will have different types of intermolecular forces, so these are just dispersion forces. These start to get some polar forces, but then these have the hydrogen bonding, which is the strongest forces of all. So the boiling points end up being way higher than expected. And even that, if we think about room temperature, only water gets high enough to be a small molecule above that is liquid above room temperature. There are very few other small molecules that are liquids above room temperature. Most others are going to be things that have larger molecular weights. And that's one reason that water is so special and has so many unusual properties and different from other things. All right, so questions about phases and boiling and vapor pressure, any of that kind of stuff? Okay, let's take a break. There's plenty more donuts if you want, and then we will talk about solutions. Yes, let me get this.